Okay, considering the fact that the determinant of A equals this is 13, the determinant of 3A, well, here's 3A, and the determinant, and working out the numbers and working out the determinant, we get 117. The determinant of 3A is equal to 3 squared times the determinant of A, because 117 is 3 squared, which is 9, times 13. 9 times this gives you this. So the determinant of 3A is 3 squared times the determinant of A. This goes back to the idea that if you multiply a row of a matrix by a constant number, you multiply the determinant of the matrix by that number. To get this matrix from this one, you got to multiply the first row by 3, and then you got to take that matrix and multiply the second row by 3. When you did the first row by 3, you multiplied the determinant by 3, and then when you did the second row by 3, you multiplied the determinant by 3 again, so you multiplied the determinant by 3 squared. If you have an n by n matrix, then the determinant of c times a is c to the n times a, because you have to multiply each of the n rows by c. Each time that multiplies the determinant by c. You do that n times, you got c to the n times the determinant. Okay, definition of a singular matrix is that it has determinant 0. A couple of properties. The matrix isn't invertible. You cannot invert it, meaning you can't reduce the matrix to the identity and other things. Okay, and you read your book, you see all the equivalent things. In terms of equations, the equation ax equals 0 has solutions x that aren't equal to 0. In fact, there are infinitely many such solutions that aren't 0. And they're all different. Okay, and an example that illustrates the meaning of this is we have this system of equations. This system of equations is degenerate. The second equation is a multiple of the first by -3. So you know that the two equations have exactly the same information and exactly the same solutions. This system can be represented by this matrix equation, and that's very clear. If you multiply this row by this, you should get 0, and that gives you the first equation. Second row times the column vector gives you the left-hand side of this equation. The right-hand side is 0. Okay, well, ax equals 0. That's okay. This system is of the form ax equals 0. Where A is this matrix, x is this column vector, and the 0 vector is the 0 column vector. So this is the system. This matrix equation has this form. The determinant of this matrix, okay, is clearly non-zero. You get -24 here, and you're going to subtract -24 here, which is going to give you 0. The solution to this system, any x vector where x2 equals -1/2 x1. Because if you go back to the equation, solve for x2, you get 4x2 equals -2x1. Divide both sides by 4, you get x2 equals -1/2 x1. Solve this equation, you get the same thing. So any two numbers, x1 and x2, satisfy this property, meaning you could pick any number you want for x1, multiply it by -1/2, you get an x2 that satisfies the equation. That gives you a vector. For example, if x1 is 2, x2 would be -1. The vector 2, 1 is a solution to ax equals 0. You can multiply it out. Multiply this by 2, 1, to -2, 1, 1, -2, it's going to give you 0. The 0 matrix. If you multiply, okay, there are infinitely many numbers you can choose for x1, giving you infinitely many pairs x1, x2 that satisfy the equation. So right there is an illustration of this property. These things are all important, and they're important properties of determinants, and not too difficult to understand.